In the last video, we developed a bunch of mathematical machinery to be able to do arithmetic on vectors. And now with that in place, we can go ahead and use that to start to extend our kinematics that we developed in one dimension into two. And the beauty of it is that the definitions are the same. So for instance, we'd said before that velocity was the displacement over the time, or if you prefer, you can write a d for displacement, but I prefer the classic delta r notation. But notice here what this is. First off, this is just plain 1 over delta t is a scalar. So this is taking my delta r, multiplying by 1 over delta t. So all I'm doing here is taking my displacement, multiplying by a scalar. And so it turns out that, yeah, we can handle this in components just fine. More on that in the next video series. And by the same token, the definition for acceleration, we remember, was the change in velocity with respect to time. And again, for exactly the same reason, this will make things work super cleanly in components. But I thought here it would be worth exploring the acceleration definition especially, and what this would mean in light of something moving in two dimensions. So let's take a look at first just plain having something moving in one dimension. We'll just have it speeding up. So let's have a car. And we'll have it speed up with respect to time. There we go. I could probably just copy and paste my car, couldn't I? Awesome. And let's move this car to the left a little bit. There we go. So here's a car. We can say it's starting from rest. Why not? And we know it's speeding up. So let's just take this all the way from the motion diagrams and see if we can figure out what the acceleration looks like. So our motion diagram is going to look something like this. So my initial position here is just plain at the origin. So you can just draw a dot if you want, or whatever for r0. And then my next position here would be this vector here, r1, and then r2, and then r3, like so. So we could find the velocity over this interval, right? We know that the velocity of something is equal to the change in position over the change in time. So over this interval here, we'll call this interval, so for this interval here, this would be r1 minus r0. There we go. Over delta t. All right, let's just do that graphically. So this would be r1, and I would add to that negative r0, and I'll do that by tail to head. Since it's just a dot, there you go. So there's my delta r. We'll do a couple more examples. But the idea here is we then remember that v is delta r over delta t. So what we'll get is a vector that points in the same direction as my delta r. And its length will be proportional. But remember, when you're drawing it, it doesn't have to be the same length because the units of velocity are meters per second. The units of position and displacement are meters. So as long as this is proportionate to that, that's all we can ask for, because anytime you change units, you automatically change scale. Okay, let's do it. We'll call this V1. All right, now let's do this again. Let's look at this interval here, R2 and R3. So we can do the same thing. We can add negative R2 to R3. So at a different interval, we'd be saying that our velocity was R3 minus R2 over delta t. So let's see what that's going to look like for us. So I'm going to go ahead and draw our R3. Holy cat, that's a long one. And then we will add to it negative R2. Something about like that. Now, technically, I should be laying the one right on top of the other, but if I do that here with everything just pointing parallel and anti-parallel, it's going to look like a mess. So, anyway, we are left with this being our delta r here. And so again, our velocity will just point in the same direction, but it'll be proportionate to whatever scale we had before. So we can just go ahead and call this V2. Okay. Now if I wanted to get an acceleration, let's see here, I should probably, sorry, that's really V3, following the notation we have. So let's just do still one more just to be comfortable with it, and then future ones will go a little quicker. Let's just do the one for the interval R1, R2. So that would correspond to, I would have my R2 here, add to it my, something like that, I guess, my negative R1, to be left with my delta R there. And so my velocity would have been a little shorter yet. So this would be my V2, let's say, something like that. There we go. Now, let's say I wanted to figure out the acceleration at this point right here. Well, on the one side, we've got my V3 would represent an average velocity somewhere in this interval. My V2 would represent an average velocity somewhere in that interval. So let's just go and find the acceleration using those. So remember, the acceleration is the change in velocity with respect to time. So we'll just say it's V3 minus V2 over delta t. So there's my V3. I will add to that negative V2. That gets me my delta V. And then since I'll be taking my delta V and multiplying by 1 over delta t, which is a positive number, my acceleration will be in the same direction and proportionate. It doesn't have to be the same length as long as it's proportionate. So what we see here is, like we were looking at before, if we're speeding up, the velocities we saw were always pointing to the right, and the acceleration is also pointing to the right. Alrighty. Let's do another case. We'll be a little quicker about this one. Let's go and take a look at a car slowing down to a stop. So here, let's just start with the motion diagram. That will make things go a little easier for me. It'll just mostly be worried about this interval here. So we know that in this interval here, the velocity in this interval is going to look something like this. So we'll just say that's my v naught, and in this interval will look something like that. So we'll say that's my v. So these are the velocities at the times flanking the time I care about. So we can again say that the acceleration is the change in velocity over the change in time. So this will be v minus v initial over the change in time. And so let's go ahead and draw it. So here's my v, like so. And I will add to that my negative v initial. Again, just doing it by tail to head. And technically I should be laying the vectors right on top of each other, but then it'll be really unclear to see. So then this would be my delta v, and we know that the acceleration has to be proportionate to my delta v, but pointing in the same direction. So this is like we saw in the previous video series. If I'm slowing down, the velocity and the acceleration are anti-parallel. Okay, but there's more that we could do than just that. We could imagine, say, having something move around in a circle. So let me just draw in a quick circle just to help guide us here. Okay, and then there we go. There we go. Draw in some points on the circle, and I'm trying to make them evenly spaced. There we go. So let's say we want to figure out what the acceleration is at this point here. The recipe is going to be come up with the velocity in the interval before and the interval after. So to do that, we're going to have to find our change in position. So let me just go ahead and put the origin of our coordinate system in the center of the circle. That will hopefully make it the easiest. So then this vector here, okay, so apparently I didn't put my origin in the center of the circle. Now it is. So this vector here, we'll say is my r naught. And then this vector here would be my r1. And this vector here would be my r2. All right. So let's first work on finding the velocity in the interval before this dot here. So to that end, we can remember that the velocity is the change in position with respect to time. So this would be r1 minus r naught over delta t. So let's go ahead and do the whole r1 business. There we go. There's my r1. And then we'll add to that negative R naught. Trying not to include the circle in this. I'd have to do this. There we go. So this would be my R naught, but what I want is negative R naught, and I can do that by flipping the vector. And then I will go ahead and put the tail of this to the head of that, just to add by the tail to head rule. You could totally use the parallelogram rule if you prefer. And so then this works out that this right here is my, we'll call it delta R naught. So my V naught will be proportionate to that. In this case, I'll just make them the same length just to make it a little easier to think about. All right. We can then go, so here we're going around at constant speed. You can see this because we're covering the same distance in the same time. We can then go and repeat this exercise for the other pair of points, R2 and R1. So we could also just as easily say that V is delta R over delta T. So this is R2 minus R1 over delta T. So again, we can, let's copy that, paste that. So there's my R2, and then, oops, I don't really care about the arrowhead if I don't get it. And then what we'll do is we'll make negative R1. Since R1 points up and to the right, negative R1 points down and to the left. And again, I'll just use tail to head on this. There we go. And so then this would be, we'll call it my delta R1. And similarly, the velocity is proportionate. In this case, I'm making the proportions 1 to 1, just for simplicity's sake. So this would be my V1. Alrighty, so finally, we can get the acceleration. The acceleration is going to be the change in velocity with respect to time. So this will be V2 minus, sorry, V1 minus V naught over delta T. So let's go ahead and do that. So first we'll just grab that, I think. So there's my V1. So this is my V naught. So we'll be wanting to negate it anyway. So V naught pointed down to the right, so negative V naught will point up and to the left. And then here, whoops, sorry about that. Here we will try to, I think we're just going to have to grab the line again. There we go, copy paste. So my V1 points down and to the right like that. So then let's go ahead and do tail to head with this. So I'll go and put the tail to the head. Boom, there we go. And so then this will be my delta V like so, and then the acceleration has to point in the same direction and be proportional. All right, so just for the grins here, let's go ahead. There. So just for the grins, after I move everything, there we go. Let's see where our acceleration ended up pointing at that point. If I put it back on the diagram, we see that it points bang back to the center of the circle. So we've seen before that acceleration and velocity could point any which way, and in 2 dimensions that is really true. It is truly any which way. But how can we decode this? And the clue is, when we were changing our speed here, the acceleration was parallel if we were speeding up and anti-parallel if we were slowing down. Here, if we're going at constant speed around a bend, the acceleration points into the center of the circle. And so what we get is that the parallel components, parallel or anti-parallel components of acceleration are associated with a change in speed. And the perpendicular components, I should just say component of acceleration, and instead of R, that should be is associated with a change in direction. So that's one of our big takeaways for how velocity and acceleration get related. One of the other things that we pick out of this is that if we took a look at my velocities, let's just go and transport one of these back here, say this one. Again, trying not to pick up the other stuff. Yeah, perfect. It turns out that my velocity is always tangent to the trajectory. So it's always tangent to the trajectory of the object. Alrighty, in the next series of videos, we will take a look at some of these things numerically. So catch you in the next ones.